Hi guys, this is Anika and Lauren, and today we're going to be talking about Bernoulli's equation, and then after I talk about that, Lauren's going to be talking about Torricelli's equation. So yeah, we can get started.
Okay.
Okay, so what does Bernoulli's equation represent? So Bernoulli's equation is basically representing the balance and the relationship between velocity, pressure, and the height of a fluid along a streamline. So you can think of this like water running through a pipe or a hose, sometimes water running through a tank of some sort, and it doesn't have to be water, it's just a fluid, but it's kind of easier to just imagine water. One main thing is that Bernoulli's equation employs conservation of energy, so the same way that we related height and velocity of like a ball rolling down a hill, this is relating the velocity, the pressure, and the height of a fluid. And it's still employing conservation of energy. But obviously, for conservation of energy to work, there must be conditions. So in this case, conservation of energy and the whole equation can really only be applied with incompressible fluids, as well as no friction. So there can't be any friction on the surface of like the pipe or the hose. Okay, so now we're kind of gonna look into the equation. So we have it here, and I've sort of dissected it into three parts. So static pressure, dynamic pressure, and hydrostatic pressure. Um, and basically what it's saying is all three of these pressures of the fluid um, remains constant. So if one increases, the other two probably decrease. Like the sum of all of them, like, is always the same as like conservation of energy generally tends to say. Um, so yeah, and then looking even deeper into the equation, so we have like the big P, which is like the pressure of the fluid, and a lot of times that is what people are trying to calculate for, like how does the pressure of the fluid change? So that's an important one. And then there's the density of the fluid. So this is why it's not always water. It can be different fluids with different densities. And this is also referred to as rho, if anyone knows what that is. And then there's also the velocity of the fluid, how fast it's moving, pretty self-explanatory, the height of the fluid, and then the gravitational acceleration, which is usually the same if it's on Earth. And again, these are all remaining constant. Okay, so now where can this be used? So again, conservation of energy, which means you can set the equations equal to each other. So again, very similar to how we do like mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared at like two different points in time. Same exact thing. You can set the equations equal to each other and then solve for certain variables. So now we can look into an example of that. Or sorry, first there's a diagram, and then we'll look into an example. But this is a really nice diagram because it kind of shows how, the water's moving along the streamline, and you have like point one where you have pressure, velocity, and density, and then point two again. And so in this case, a lot of times when like the thing gets thinner or like the pipe, the pressure changes. So in this case, they could solve for the changing in pressure or the changing in velocity depending on what values you're given or values you know. So yeah, this kind of demonstrates how like they from point one to point two, the overall sum of all the different pressures stays the same. Okay, so now we're gonna get into an example and we're gonna chop some onions. So um, say that a hose has frictionless flow. So again, the surface has no friction, and the velocity of the water changes from 1.96 to 25.5 um, meters per second when it transitions from the hose to the nozzle. And so in this case, we're trying to calculate the pressure in the hose, um, knowing the pressure of the nozzle. So we're basically just trying to find how does the pressure change from point A to point B with point A being the nozzle and then point B being the hose. And then again, we're assuming level, which means there's no compression, and frictionless flow, which means that we can apply conservation of energy. Okay, so one thing to keep in mind before we get into sort of the solution of this problem is that a lot of times when you're looking at these problems, they just won't include the height part, like the pGh in the equation, because the height of the liquid only changes if like the pipe is actively like going upward or going downward, like the height of the liquid is changing. And so in the problem that we're looking at, like we're assuming that like everything's at the same level. There's no like changing in height. Which is why when we get into the solution, you'll see that that height part is just like not considered because it stays the same. So yeah. Okay, so again, bringing back to that earlier thing I had brought up, we're looking at the pressure one, velocity one, density one, and setting that equal to pressure two, density two, velocity two, and height two. But again, we're disregarding that pGh part as I explained, because in this case, the hose is just like at one level, it's not going up or down. And so we're gonna solve for P1, and then you get sort of like this equation when you move the other things to the other side. They gave us the velocity 25.5 meters per second, 1.96 meters per second. Um, they gave us one of the pressures, so like P2. And so that makes it pretty easy to solve for the pressure that we were looking for. And we get this answer, and you can like obviously try this in your calculator. But yeah, this is a pretty like standard example of how you can plug in numbers, set things equal to each other, and figure out changes in pressure. If they had given us the pressure but not the velocity, we could have done changes in velocity, and yeah. And now we're going to be moving on to Lauren's part.
All right, hey guys, this is Lauren, and I'm going to be talking about Torricelli's equation today. And this is going to be a little bit shorter because Torricelli's equation is actually derived from Bernoulli's equation. All right, I'm going to move us up here. So, what is Torricelli's formula? Torricelli's formula is a formula in fluid mechanics, and it's, of course, named after Italian physicist and mathematician Evangelista Torricelli. And we have a little picture of him on the right. And so, this formula relates the velocity of fluid flowing out of a small opening at the bottom of a container to the height of the fluid above the opening. And like I mentioned, it's derived from Bernoulli's principle and is commonly used to analyze fluid flow scenarios. All right, and then here I have Torricelli's equation. So it is V equals the square root of 2 times gravity times height. So V is, of course, the velocity of the fluid flowing out of the opening. G is gravity, so 9.8 meters per second squared on Earth. And then H is the height of this fluid surface above the opening. Um, and then I have a little diagram here just to explain height a little bit. Here I have my container filled with whatever fluid, and I have my hole at the bottom and it's of course leaking. So my height would be from the point of my hole to the top of the fluid. And this equation assumes that the fluid's velocity at the opening is solely due to its potential energy, and it neglects other factors such as friction, assuming the fluid behaves like an ideal fluid. So just like how Anika mentioned, this is kind of conservation of energy, and we are basically just assuming that this fluid is an ideal fluid. All right, and then we're going to move on to an example. So my example is a water tank has a small hole at its bottom. If the water level in the tank is 5 meters above the hole, determine the speed at which the water exits the hole. And then I have my diagram here. So we know that the water level in the tank is 5 meters above the hole. And like we had said, our height is the point from the hole to the top of the water or liquid level. So that is going to be 5 meters for our height. And I have a little diagram here again. And then as usual, our acceleration due to gravity is just going to be 9.8 meters per second squared, as long as it's on Earth. And then next, we're just going to plug in our given values into our formula. So we have V equals the square root of 2 times 9.8 gravity times 5 meters, which is our height. And when we calculate that, just plug into your calculator. We get velocity equals the square root of 98.1. And when you square root that, we get our final answer of 9.9 meters per second. Um, yeah, and that's going to be our velocity. And thank you. That's kind of all we have today.